Hello guys, welcome to Maths with RM. Let us start discussing logarithms. A very basic chapter of the section of algebra. This particular operator of logarithm is important because this is used in various chapters of maths as well as in sciences, and it is one of the most critical operators of mathematics. This operator has a complexity in the sense that when you turn an exponential expression to a logarithmic one, it becomes easier to operate with. To begin with, let us start discussing what exactly a logarithm operator is. This is how it goes. Say, for example, if you write a power y is equal to x. If you say a power y is equal to x, this is as if you are describing an expression in y as a resultant in x in terms of y. Now, can we do the reverse? Yes, we can do the reverse. That means we can describe y purely in terms of x. That means y can be written as equal to log x base a. If this happens, then this happens, and also vice versa. That means a power y equal to x has an alternative expression in y equal to log of x base a. Now, this particular operator of log has some basic limitations of operation, like to begin with, let's say if we want to test this operator working on numbers, let's say on what numbers this log operator can operate on. Can it operate on negative numbers? So let us try. Let's say we are trying the log operator as if y is equal to log x base a on or for x element of a real minus x element of real negative. Now, if we do that, let's say we take a testing number. Say, for example, we want to operate, let's say, log of minus 4 with a base of 2. This is just for an example. Let's take this just as an example. If you want a y value in terms of log of minus 4 base 2, that means alternatively you should have 2 power y equals minus 4. Now, is that ever possible? Answer is no. This is not possible. This is not possible. An exponential expression cannot have a negative value. And that means if this is not possible, that means this is also not possible. This alternately implies this is also not possible. And hence, rule number 1, log never operates on negative real values. This you can say is a rule of log. You can also try yourself on any negative number of your choice with the base of your choice. You can put minus 8 here, you can put 2, or you can put minus 16 here. Again, you can put 2, you can put minus 100 here and a base of 10. You can make a choice of your convenience for the negative number and the base, and you can try. For this particular operation, you will find that log will never operate on negative real values. This is point number 1. Now dear, going ahead, does it operate on 0? Let's try on that. If you say y is equal to log 0, log of 0 base 2, that would mean 2 power y is equal to 0. Now this is not possible again. Why? Because if you take y tending to minus infinity, if then you can say 2 power y can become as good as 2 power minus infinity. This can tend to 0 but cannot become equal to 0, dear. That means log 0 base 2 has no real finite value. Log 0 base a, you can say with a generality. You can say with a generality that log 0 base a, this entire thing has no real finite value. In that case, this would stand as equal to a power y. And still y would tend to minus infinity. This would be like a power minus infinity tending to 0. So log does not operate on negative real numbers. Log does not operate on 0. It produces no real finite value. Then what does log operate on? Question is, then what does log operate on? Log operates on positive real values of x. The answer is log operates on positive real values. This is what it operates on. Point number 3. I hope all of you are till now comfortable with what I am saying. And that means you are clear about what log can operate on. You can select the permissive values of x on which log can operate. Now, let's look at the base. Let's look at this base. And how do we pronounce this? Most importantly, how do we pronounce this? We pronounce this as log of x base a. This is how we pronounce it. Log of x base a. Now, let's take some specific values of the base and let's play with the log operator once again. And we can do it right here. Let's say, now let's take point number 4. Let's take a base. Let's take a base which is negative. Base equal to negative real number. Let's say, for example, if we take the base of log value, base equal to a as equal to, let's say, minus 2. Now, what will happen is, say for example, you are operating on log of 4 base minus 2. You will surely get an answer 2. This is perfectly alright. Now you take y equal to log of 8 base minus 2. What are you going to get the answer as? This would mean minus 2 power of y should be equal to 8. Is this ever possible? Y equal to 3, if y equal to 3 is taken, it would produce a minus 8. This equal to 8 would never be attained. This is not attainable, and hence that means log with a negative base sometimes operates, sometimes doesn't. Base equal to negative means not acceptable. This is not acceptable. Think on this. So, therefore, base of log cannot be negative. Base of log cannot be negative. Let's go to another and let's keep this noted. Let's keep this noted that base equal to negative, base not equal to negative. Oh, sorry. Let's keep it equal and let's say separately that base of log cannot be negative. First of all, it cannot be negative. There are more types of values of base which are not acceptable. Let's take one more example here, dear. Let's take one more example over here. Can the base of log be 0? You can instantly make a thinking over here. Base of log, if it is equal to 0, then what would happen? Now see, dear, point number 5. If base becomes equal to 0, and think on this, you are talking about log 4 base 0, and that alternately means 4 is equal to 0 power y. I hope I am correct. X equal to a power y, 4 equal to 0 power y. Now see, this is not possible, and that means base of log cannot be 0 also. Cannot be 0. No, not correct. Not correct. Not acceptable. Not acceptable. Again, not acceptable. And then a last trial on base of log equal to 1. can base be equal to 1? Think on this. A equal to 1. And let's try y is equal to log 4 base 1. Oh, that makes 4 is equal to 1 power y. 4 equal to 1 power y. That's not happening, man. That's not happening. No way. And therefore, base of log cannot be unity. And unity means 1. Base of log cannot be unity, cannot be 1, cannot be 0, cannot be negative. Then what can base of log be? Good question. If you are thinking in these lines, then you are asking a very good question. Base of log can be either greater than 1 or it can be between 0 and 1. These are the two acceptable base inequalities about logarithm. Let's go ahead. Let's operate some things and then see furthermore as to what log does with different types of bases. Let's say for the base value between 0 to 1. Let us select a very convenient base value, say for example half. And when you talk about base greater than 1, let's take a convenient value, let's say base equal to 2. So let us make some simple operations on how the logarithm operates if the base is equal to log of x base half. This is just an example here. This is just an example. And if you take different values of x, we are just going to have a look at how the log operator behaves. I mean on the graph. I mean variation of y with respect to x. Let's do that. So let's plot the values of x and y simultaneously one over the other. Let's say x is equal to 64. If x equal to 64, that means you are talking something like this, that x is equal to half power of y. And if x equal to 64, that means x equal to 64, that means you're talking about 2 power 6 and should be equal to 2 power minus y. That means y turns out minus 6. This is how we evaluate the corresponding values of x and y. So this y should be minus 6. Similarly, at 32, you'll find this minus 5. At 16, you'll find this minus 4. At 8, minus 3. Y value is minus 3. At 4, it is minus 2. See how linearly it is decreasing, and these are log values here. And when x values are exponentially decreasing, you see the log values are linearly changing. The change in x values are geometric in nature. Change in y values are linear in nature. I mean they are going down or going up one step at a time. Plus 1, plus 1, plus 1 and so on. Let's take 2. Log 2 base half is going to be minus 1. Then 1. Let's try at 1. Log 1. Log 1 base of anything there is going to be 0 because half power 0 is 1. So this is 0, y value is 0. And if you go at, let's say half, you are at 1. Then at 1 by 4, you are at minus, no, 2 plus 2. And like this, 1 by 8, you produce a 3, y value 3. And that means when you plot the graph, it would look something like this. Let's take a graph. X-axis over y-axis. You are not going to take negative values of x as we had discussed earlier. And you are going to scale x values from 1 by 8 till 64. Now, it's not really possible in this very small space, but I will try to accommodate as much as possible. Let's say we begin with an origin here at this point. And let's say if this is 1 and if this is 2, this is approximately 4. Let's see what happens in this small region. And if this is 1, then this is going to be half. This is going to be 1/4. and this is going to be 1/8. Now, if you take positions on y-axis, then for this 1/8, I am at 3. That means I am at 3. Let's say 3. This is plus 3. This point is plus 3. Then at 1/4 I should be at 2. And if this is 3, let's say this is plus 2 and this is plus 1. And let's say this minus 1, this is minus 2, and this is minus 3, and this as minus 4. Now let's go ahead with this. Let's try to plot. At x equal to 1/4, I should be at 2 here. At x equal to half, I should be at 1. I should be here. And at x equal to 1, I should be at 0 here. Y equal to 0. Then at x equal to 2, I should be at y equal to minus 1. Here it is. At x equal to 4, I should be at minus 2. Let's jump to the point and let's see what happens. This is what happens. And the graph goes smooth like this. This is the graph for y equal to log x base half. This is how the graph looks like. Then let's go to the next point as to how would a general log graph with a fractional base look like. It would be a decreasing function and it would decrease just as it happened just now. Y equal to log x base a. A is, let's say, a fraction. This is a fractional base. And how would the graph look like? The graph simply looks like this. Cuts x-axis at 1. At 0 plus, I am at plus infinity and gradually declines. Ahead of 1 on x-axis, it declines to negative values and this is how it goes. This is a fractional base log graph. Now dear, let's try the same experiment with the base value greater than 1. With the base value greater than 1, let us take a simple example. Just we had taken as earlier log x base 2. In this case, let's take an example of plotting x against y. And the same types of results would generate. Let's say we begin with x equal to 64, that means log 64 base 2 is going to be 6, log 32 base 2 is going to be 5, 16 base 2 is 4, and then 8 base 2 is 3, and 4 base 2 is 2, and log 2 base 2 is 1, and log 1 base 2 is 0, log half base 2 minus 1, log 1/4 base 2 is minus 2, and so on, so on. It goes on. Let's plot this. If you plot this, we are sure that we are not going to work on negative x-axis. The working will begin with 0 and ahead. This is your y-axis, and now dear, it goes like this. Let's plot the points. Let's say this is exactly 1, and let's say this is 2, and let's say this is 3, and not more than that we can accommodate here. And if this is 1, take a 50% position, another 50%, another 50%. Now, at 1/8, where did I stand? Where should I stand? At 1/8, I should stand at minus 3. Oh my God. Minus 1, minus 2, minus 3. At 1/8, I'm standing at minus 3. At 1/4, I'm standing at 2. Minus 2, sorry. At half, log half base 2, we are standing at minus 1. At 1, exactly at 0, log 1 base 2 is 0. I hope you can follow. And then the graph is rising like this at 2 plus 1. This level will be taken at 2. And then at 3, possibly you're going to have a little higher value. How will the graph look like? This graph looks exactly the negative of what had been there earlier, and that means it's a rising graph, it's an increasing function. It's an increasing function, and this is a general trend for log x base a for any a greater than 1. That means a base larger than 1. This graphical nature will persist, and I hope you're now clear about how a log graph looks like. There are only two types of log graphs. Only two types, and we have discussed both of them. The log graph is an extremely important tool, you can say your equipment, to deal with logarithmic inequalities. We will discuss with that a little later. For now, let's stay focused on properties. Properties of log. I will go comparatively slow so that you can focus on the dynamics of the properties. I'm going to deal with very simple things, and let's begin now. Let's say if you define a power y, if you say a power y is equal to x, then you are saying that y is equal to log x base a. Now listen very carefully to what I say. If y has this value, can I replace this y back here? Answer is yes, you can, safely. And that means, what does it produce? A to the power log x base a equals how much? This same x. This becomes the definition of log operator. This is definition of the log operator. A power log x base a equal to x. That means, for example, just as an example, 3 power log 5 base 3 is going to be straight 5. This is how it operates. Property number 2, log never operates on negative real numbers. Also on 0. That's all. Log operates on, you can say and on 0. Log operates on x greater than 0. Simple. Point number 3. Base of log cannot be negative, cannot be 0, cannot be 1. These are not the properties. This is the summary of what you have been listening to so far. Thanks for your patience. Let's go to the properties now. Properties. Let property number 4. Let a power x is equal to p and a power y is equal to q. That means log p base a equals x, and log q base a equals 1. Let this be the considerations. Let's begin with property 4 now. How about this? How about taking a product? Take a product PQ. That means you're dealing with a power x dot a power y. That makes a power x plus y. That means PQ product is equal to a power x plus y. And hence, this being an exponential description of the relations between these product and the sum, we can convert this to the logarithmic form. And the logarithmic form operation would look like this: log of PQ base A. This base of the exponential turns to the base of log. I repeat, base of exponent is the base of log, is equal to x plus y. This is your x, this is your y. That means log PQ base A is equal to log P base A plus log Q base A. This is called product rule of log. This is called product rule of log. Let's go to the next property, property number 5. Just as we had taken product, let's take a ratio, P by Q. That means you're talking about a power x upon a power y. I hope you are clear. A power x by a power y is equal to a power x minus y. This is an exponential equation. Let's convert these to an logarithmic one. That means log of P by Q base A is equal to x minus y. This x, this y will be still used. That means log of P by Q base A is equal to log P base A minus log Q base A. This is called the quotient rule. This is called as the quotient rule of the logarithms. I hope, dear, you are clear till here. Let's go ahead. Property number 6. Property number 6. What can that be? You have taken the product and quotient of P and Q. Now, in this sixth case, say for example, this a power x equal to p. If you want to rewrite that, then from here you can write a is equal to p power 1 by x. And from here you can write that same a is equal to q power 1 by y. 1 by y. Then p becomes equal to q power x by y. This is an exponential equation. Let's convert this to logarithmic form. Log p base q equal to x by y. The same x and the same y. That means log p base q is equal to log p base a by log q base a. What exactly is this? Log p base q, log p base q, old base q is equal to log p base a by log q base a, new base a, new base a, new base. Yes. This is the way we can change base. This is called the base changing rule. This is called the base changing rule. Now how to use this? The way you can use this is something like this. Say for example, you are given log 64 base 4. What should be the answer? 4 cube is 64. Therefore, the answer should be 3. This is perfectly alright. Now let's say I want to change the base to 2. Then this same thing can convert to log 64. Now remember, log p base q, log 64 base 4, log 64 base 2, log 4 base 2. Log 64 base 2 means 6. Log 4 base 2 means 2. It's still going to produce the same 3 as earlier, and then you can say that just as this is writable and this is writable, they are interchangeable. You can convert this to this or this to that. Interchangeable, it's an equation. I hope you understand. This is the base changing rule of logarithms. Alright dear. Okay, let's go ahead. Property number 7. Property number 7. What can that be? It's something like this. Suppose you write log of p power k base q. What can that become? What can that become? It can become something like this. Base q with a p power k means p dot p dot p and then p. How many times? K times. Oh my god. Not good. We had earlier seen that log of pq base a is equal to log p base a plus log q base a. We use this rule, the product rule of logarithms. Let's use this. Product rule of logarithms. Let's use this. What if q suddenly becomes p? Let's see, if q becomes equal to p, then what's going to happen? P square log p square is equal to log p base a plus log p base a. That means log p square base a is equal to 2 times log p base a. This becomes p, this is p, log p base a, log p base a, 2 log p base a. And if suppose this is 20, then this will become 20. And what if this becomes k? Then this becomes k, and that means this product is going to get converted to sum and sum of log p base q k times, and hence we can say log p power k base q is equal to k log p base q, and that means the power is going to get shifted as a numeric coefficient or multiplier, and then you can say this is the power rule, the powerful rule of log. Let's go to the next rule then, rule number 8. Property 8. Oh my god. Log p base q with q power k. Now k is to the power of base. Now here we can use the base changing rule. The base changing rule can go like this, dear. Log p base a by log of q power k base a. That can become log p base a by k times log q base a. That means effectively you're going to get 1 by k out of the power of the base as a denominator number, 1 by k into log p base a by log q base a. and that becomes equal to 1 by k times log p base q is equal to log p base of q power k. Observe this. Say this. Property 8 done. Let's take property 9 right here in a small space. Property 9 inspired by property 8. What if I have log p power n base log q power k? Can you guess on this? This power rule applies to this power rule applies, n goes to the side. Or if you want to change base, how about this? Base a by applying the base changing rule, you get log of q power k with a base a. What does that make? N to the side, k to the side, n by k. Log p base a by log q base a. That makes it equal to n by k into log p base q. See here, this is property number 9. Here itself, we can have some space for property number 10. Here. Say, for example, you are given an expression like this. A to the power log b base k. Can you think? We can also write this as b power log a base k. This is the 10th property we are going to prove now. But see the magic. A and B interchange their position, retaining the equality. Straight on the face. Juggling. That's log. It works like magic. Alright, let's go to prove this property number 10 right now. Right now. On your copy. On your copy. With a pen. And then let's go ahead. Property number 10. With a pen. On your copy with a pen. Property number 10. Oh my god. A power. Log b base k. Let's say this is equal to y. Y. Now apply log on both sides. Now apply log on both sides. Log b base k. This base looks like k. Let's keep it k. Let's keep it k. Since this is k, we provide a base k. Now we can apply power rule here. Log b base k and log a base k. Dear, this thing shifts to the side, makes it like this. This one goes separate out, and then we have log y base k still alive, kicking, and on the left side. Now, it's like 5 into 9. I can also write it as 9 into 5. 9 into 5. Log a base k, log b base k. This can go to the power, and then it can become log b base k with a power. Log a base k. Ha 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 ha. And what do we have here? We still have log y base k kicking alive. How is this? Bad, very bad, so sad. That means y is equal to still b power log a base k. Oh my god. It was something like this. It became suddenly like this. That means a to the power log b base k is equal to b to the power log a base k. Think on this. You just proved this. See you in part 2. Thanks for your patience. See you. in power 2 by Rn.